In this video, we're going to perform an analysis on the deflection, effective stress, and impact on a springboard using Ansys Static Structural Finite Element Analysis. To get started, let's take a look at what a springboard is. They are used in Olympic diving competitions or other world or other local competitions. And the one that we're concerned with is typically 3 meters above the water, at least for Olympic competition. And you can see that the divers are on the ends when they have their liftoff, and they get to a significant height. This height they achieve by jumping at least once. So you can see that this diver, right, is able to jump much higher than they would able to jump with just a standard static takeoff, because they put energy into the board and then they use their legs to spring up even further. So they have essentially a trampoline type effect. And if you look at the height that this diver is able to achieve, it is quite significant. I mean, it looks quite high because they've tucked their legs in, but even if you go back to here or here, okay, well, maybe not that far, okay, this diver is significantly higher than they would be able to jump just from a standing static jump. So let's say, it's a meter plus. And that height that they are jumping to is going to affect the impact that they have on the board when they come back down. So when they come back down, we can get significant deflection of the board and significant stresses. These boards, though, are designed and engineered to be able to handle this type of loading. And so we're going to have an opportunity to see how much stress do we expect that these boards are going to be experiencing under different conditions. The board used for Olympic competition comes from a company called Duraflex, and doing some searching on the internet, I was able to find some parameters. The length of the board from the back, or from the back to the front, or front to back, is about 16 feet or 4.9 meters. The width, the top of the board, is about half a meter. The thickness of these boards is about 2 inches, and they're made from aluminum 6070 T6. This material has a significant yield strength, pretty high for aluminum, and the elastic modulus, of course, is what you would expect, around 70 gigapascals. There is a fulcrum that is adjustable by the diver to allow them to change the feel, the stiffness of it, and often they run it back so that the distance is 1.55 meters from the back to the fulcrum. It comes centered, or if it's centered in this box, it will be 1.88 meters from the back end. For this demonstration, we're going to use 1.88 meters. So what we're going to do is bring this geometry into Ansys, and we're going to also perform some analyses based on what we might have studied in mechanics and materials or solid mechanics for a simply supported beam at 2 locations with an overhang. And if you go to this website, you'll find the formulas that give you the bending stress, that give deformation. Okay, and this is assuming that we have a beam and that the deflections are pretty small. We'll compare some of these calculations to what we get in Ansys, and then we'll go further and do an impact factor analysis or impact analysis to be able to see how high the diver might need to get themselves in order for the beam to have a certain deflection, or to induce a certain amount of stress, or to think about the amount of potential energy that is involved in the system. So let's go ahead and go into Ansys now, and we're going to go File, New. Okay, no, we don't need to save it. And let's do the simple part of inserting the static structural component system into our schematic, and then going into the engineering data, and we're going to create a custom material here. We'll call it AL6070T6, and we will go ahead and insert the properties that are important to us. So density for the simulation is 7850 kilograms per meter cubed. We can also insert the isotropic elastic properties, which are going to have a Young's modulus close to 70. We're using what the manufacturer or what MATLAB is providing, and a Poisson ratio of 0.33. We're not going to input the yield stress or yield strength into this model at this point, but we will keep that in mind as we do our analysis. It's often a good idea to set the default for this new material so that we don't accidentally get the Ansys default into our model. Let's go ahead and open up Design Modeler for this case, and we're going to do a 3D simulation with the rectangle and a thickness. Now, something to keep in mind here is that we want to be able to also specify a fulcrum location. That's 1.88 meters away from the back end of the board. So for doing this, I found that Design Modeler made it a little bit simpler to create a line on which we can apply an appropriate boundary condition. To get started, we'll click on the Z, and we will go ahead and start sketching by creating a rectangle. And we're going to create a rectangle of the portion from the back of the board to the fulcrum here, okay? And so that's the 1.88 meters, and then we'll create another rectangle going from this fulcrum to the diving portion, okay? The front of the board, I guess we can call it. So for this, in Design Modeler, we create our rectangle, we click, we get a P, and we'll put it here. We'll go ahead and put in some dimensions. The horizontal dimension we'll use from here to here is going to be 1.88 meters. The vertical dimension from here to here is going to be almost half a meter. So that will be 0.498 meters, just like that. And then we'll go ahead and we'll add another rectangle here. Draw rectangle. Okay, we get the P, good. Okay, get the C, and we'll create a dimension that gets us going from here all the way to here, and this one should be about 4.88 total. Okay, so this region is about 3. Once we've created this geometry, we can go over to the modeling portion, and we can make lines from these sketches. We can select all these, box select if we want, like this. Okay. Actually, before I do that, I'm not going to do that. Sorry. We're going to first go back into sketching. Whoops. This leads to a problem. So we're going to go ahead and delete that. Yes. Okay. And we're going to go back into sketching, and we're going to trim. I apologize. Okay. These pieces out. So just delete, and there are 2 here. Delete. Okay. So we have these points here, but they are now there's now no longer a line, which allows us to create the surface. This is a little tricky. Okay, so now we're going to do, well, we can do, this is fine. We can do surfaces from sketches, okay, and we're going to go ahead and select. This is a box select. We'll select all of this. Okay, we'll hit add, and then we'll hit generate, and that is our nice surface. Once we've got this, we can then extrude this surface, okay, and we're going to apply it to this geometry. Okay, we can do it this way, yeah, okay, apply, and then we're going to do a height of 0.0508, like that, and we're going to hit generate, okay, and it did not like that, okay, well, we're going to do it this way then. We'll do the extrude directly from the sketch. Okay, and we will select this sketch, apply, and now we will do the extrude, and that did work. Okay, thank you for your patience. You can see all the little things that go wrong. Now we will go ahead and do a face split on this. So we go to Tools and we go Face Split. We click, this is the target face. Whoops, okay, that's the target face, and I'm going to actually go and just do single select here. That's the target face. We hit Apply, and then for the tool, we're going to use the vertex. Yeah, that's good. Vertex here. So we'll go from this one, and then hit Control to that one, and hit Apply. And now it's split on the bottom. We hit Generate, and we have two faces that we can use, like that one and that one. Okay, we're now done with our geometry after a little bit of mishap. And we're going to close that, and we go back to Workbench, and we're going to bring it up in our model. So we're going to mesh this geometry with quadrilateral meshes, and we're going to apply some supports. So the supports will go here and at the fulcrum, as you saw. So it's still going to take it a second, I think. So here and here. We will need to be a little bit careful with the stresses that we calculate, because there can be concentrations in close proximity to these supports. So I'll show you that how to handle that, and essentially we're going to ignore some of those extremely high stresses because they're concentrations. As the real material with bolts and washers and nuts, they're able to relieve some of these stress concentrations. It's not just at a line or a point. So if we go under geometry and solid, we see that the material is in fact our AL6070, so that's good. And we can go right to mesh, and we're going to change the element size to 20 millimeters, just like that. Okay, and we are in millimeters. You might not be in millimeters when you do that, so we can generate the mesh, and we'll see that it comes out pretty nice, and it's pretty fast, and it's pretty uniform. Okay, now where did that line go? Well, if I come back here, it's there. Okay, and that's the line on which one of the lines on which we can apply boundary conditions. So here you can do this a couple of different ways, but we'll go ahead and we'll do a fixed support just at the vertex here on this location, that location, okay? And we hit apply. And then what we're going to do is we're going to use displacement supports, okay, for this. So let's see, we need to select, I want to do on here, this here, okay, and this here. All right, and we're going to say that in the X direction and the Y direction, okay, the system, we're going to give it freedom. But in the Z direction, okay, so the diver is going to be over here. In the Z direction, we are going to say that it has to be 0, okay, just like that. For the force that we apply at the end, okay, we can introduce, sorry, it's up here. We can introduce it on this surface that we see there. So we're going to go over here and select this face. Whoops, okay, like that. All right, actually, what's going on here? Yeah, okay, there, apply, good. All right, and the magnitude for now. All right, so here we have to specify a magnitude, and we're going to use a person, okay, that has a mass of 70 kilograms, all right, to get started for our static calculation. So 70 kilograms times 9.8 meters per second squared. That comes out to be 686, okay, newtons. So we'll go ahead and we'll put down 686. And for this, we can do it in components. So let's come over here and components. And we're just going to do a z component, and I'm going to do it in the minus 686, okay, direction like that. Okay. Now, what are we interested in seeing? Well, we're interested in looking at the stresses. We can do equivalent von Mises stress, okay, across the entire body. That's fine. Okay, so this is all values. Yeah, right. Okay, so, or it was already selected, but now it's there. Okay. And we'll see something that's maybe a little disturbing when we do that. And we'll also, let's look at the deformation for now. Okay, and we'll do it directionally. So we're looking at the direction of interest being z. Okay, and let's go ahead and solve. Oops, there's an issue. What did I do for displacement? Oh, I didn't select the geometries. All right, I didn't hit apply. That's why. Yeah, that's why I was giving a little hang up here. So this, and then control, like that, those two. Now hit apply, they're in. Now let's solve. Okay, so what are we going to expect? Well, in this system, we're expecting that the board will deflect downward at this end, right? And we expect that we're going to have bending stresses on the top and the bottom of the board. And so if we look at the equivalent stress, okay, what do we see? We see that, in fact, there is, okay, there we go. That's a little bit better. Okay, you can see that there is a stress, right, a gradient in the stress across the top. Okay, and if we look at the calculations, the analytical ones, the prediction for the maximum bending moment, all right, and thus the maximum bending stress is supposed to be above this fulcrum right here, or at the roller, okay, right here. And so that can be calculated like we see here. Now, where is the maximum bending stress right now for, or maximum stress that we're seeing? Well, we can go to let's see, yeah, we can go over here to display and click on maximum, okay, and it'll tell us, okay, there's a maximum, and yeah, that's, you know, it's actually not above, okay, but it's below, and it's sometimes a good idea to say, okay, is this close to my boundary condition? And you can see, well, maybe it is, there's a sharp thing. If I click on this right here, okay, look, there's the line, click on the mesh, it disappears, click on that again, but then click on the equivalent stress, and it's right on the boundary condition, all right? So this stress might be a little bit unrealistically high, all right? So what can we do? Well, we could say, okay, that's a problem from a design perspective. For our analysis, we can also say, maybe we should limit our scope of where we are looking at stresses, all right? So to do that, let's create another stress result, all right, like this. And we can do von Mises again. And this time, what we're going to do is put it on the top face, okay? Because that's where I know I'm going to have maximum bending stresses. So I hit apply there, and it's on that face. And now we can just retrieve this result, okay, like that. And we see that it's around 10, okay, and it's right there, it's around 10 megapascals, okay? So this, you know, this one is 14, it's, you know, 1.4 times underneath, and this one is a little bit lower. And now we can say, well, how does this compare to analysis? So for that, we have some MATLAB already prepared. Okay, so here's the 70 kilogram person. Here's gravity. Here's the static deflection, all right, that we expect. There's static strain energy. We'll talk about strain energy in a little bit. And then this is the maximum bending stress. So if we run this, and I guess I've already done it, okay, the prediction using the beam bending equations is that we get 9.6 megapascals of bending stress. So we're right in the ballpark. That's quite good. All right. So that's promising. And then let's look at the deformation. All right. So the deformation, okay, right now it's giving us a max. Well, the deformation is negative. All right. So we don't want the max because that's going to be the least negative, or maybe just slightly positive as that portion of the beam goes up from the bending. So let's take a look at using the minimum, and that comes at the end. All right, and what do we get? Well, for our minimum, we get minus 26 millimeters. Okay, so minus 26.28 millimeters. What do we get from MATLAB when we do this? We get 26. It's about the same, 26 millimeters. Right. So this suggests that we have very good agreement between our analytical solution and our finite element. Okay. Now, things start to get a little bit more interesting in what we're going to do next. This analysis is for static loading, and we can calculate the strain energy that is present. There are actually a couple ways to do it. If you like, you can right-click here. You can click Worksheet Result Summary. And you can go to Available Solution Quantities, and you can come on down here. Okay, and what you'll find is that there is actually a quantity, okay, for the potential energy. Okay, it's called, and it's an expression. So you can right click on this and you can create a user defined result. So this is kind of fun. And so a UDF is allows you to do more custom things. Like I can multiply now this quantity by 1,000 if I like. All right, it's going to come in millijoules, but I'll do that in MATLAB later. But I just wanted to show you that this is a possibility to use these UDFs. So here we're going to evaluate this result, and that comes out to tell us that the maximum is the total. Sorry, we want the total strain energy, not the maximum. The maximum will be the local strain energy in an element. The total is about 9 joules. Okay, so if we go back to MATLAB, all right, and we calculate out how much strain energy there is, and how do you do that? Well, the strain energy is going to be determined by thinking about this as a linear spring and looking at the area under the force displacement curve. So it's going, yes, you're probably more familiar with 1/2 k delta squared, but also the energy is going to be under the curve is going to be 1/2 times the force times the displacement. Okay, so we can use that equation because we know what our force is that 686 newtons, and times the delta times the displacement times 1/2, and that gives us the static strain energy from the calculations, and that comes out to be 9.2 joules. And so once again, we're seeing that Ansys and our analysis, okay, this is 9 joules, they're coming out pretty close. Okay, so we've now talked about the energy associated with just a force being applied at the end. How do we think about this jumping diver, okay, and the fact that they're way above the board and they have a lot of potential energy that then transfers to kinetic energy, and then once again the diver stops as the board bottoms out, and then they get sprung up. But at that point where the board bottoms out, the potential energy is at a maximum, right? The kinetic energy is at a minimum. Where is all that potential energy? Well, it's stored in the beam. All right, that potential energy is stored in the beam. You can also say, well, you also have a change in potential energy because the diver has, they were higher and they're lower, but now it's all in the beam. All right, and that is what we consider to be the strain energy. All right, and we can think of all that strain energy, right, in the structure itself. So for this, we can go back to an oldie goldie for those who may have taken design of mechanical components or equivalent course and think about the impact factor. Okay, now something to realize about the impact factor that maybe we forget is that if I just gently put a weight on the end of an object and it sinks, all right, or it deflects, right? There's this transfer of that energy, right? That kind of kinetic energy of the motion, right? Going down until it bottoms out. That essentially, so if I have just a height of 0, okay, so I just put it right on there, this impact factor becomes 2 automatically, all right? See? Because this is the static displacement, right? Like we just calculated, we're just saying, hey, there's a force on the end, the weight of the person, the weight of the diver. But this actually, if I rest it there and then they go down, drop it, right? I don't just like let it like slowly go down with my hand holding the weight, the diver or whatever. No, there's going to be an impact factor, right? So as the diver is going through the equilibrium or the zero loaded actually point, right? There's going to be an additional amount of potential energy that gets put into the board. So we need to account for that as well, okay? But this equation, and you can look at Juvenile, you can look online, you can remember that if I know how high above a spring I am, okay, I can calculate what the effective force that is going to be applied to the structure might be. And this is very useful, even when you're doing finite element analysis, because I don't want to do a dynamic simulation right now where this thing is hitting it, okay, and then it deflects. You can do that using Ansys explicit, but right now we're going to just stay in our nice static structural world. Okay, so these are equations that will allow us to calculate what the effective force is. Once we know what the effective force is, then we can go back, right, and calculate out what the bending stress might be. So that P before was static P, but now that P is going to be a static P times an impact factor that then is going to go into our calculations for the bending stress. Okay, and it also goes into our calculations for the energy stored in the spring. All right, so now if we look at our system, we say that this diver was up very high, they go down a height h, they land on the board, and then there's this additional displacement, okay, of the impact, okay, on the board. So how far do they go down with the board? Just like if I was putting that diver there and I just let them drop, okay, I have this additional distance that's been traveled, and it is significant, and that allows us to calculate a total potential energy. And this is what's a little bit confusing sometimes with a static analysis, is that yes, we did deflect, right? But we're not considering that in our energy calculation, right? Because I didn't have the person physically fall that distance. So when we think about the total potential energy, okay, that this diver is putting into the system, we account for that height, their maximum height above the 0 line, and we account for this impact displacement. And we say that that potential energy is going to be equal to the strain energy in the system, in the board, okay, when it's at its lowest point, when the diver's at its lowest point. okay? And so if we know the strain energy and the displacement of the diving board, all right, or this deformation, this how far the diver might have gone down, we can calculate how far above they were or how high above the zero line they got, okay? All we do is we rearrange this equation. So we need to know, so U is equal to PE, so that's the strain energy U, okay? And we still have the mass and the gravity, right? Mass of the diver and gravity acting on them. So we divide by mg, and then we can subtract the impact displacement, all right? Now, this analysis can be done analytically, all right, but it doesn't account for potential nonlinearities and interesting geometries. Our geometry is arguably not that interesting, but nonetheless, if we do this analytically, all right, we can begin to get an idea of the relationships between how high the person is and the strain energy involved and the impact, the displacement that they're going to get. Okay, so analytically, if we go back now to our MATLAB, okay, what I've done is said, okay, look, let's say that the person gets to a height of 1 meter above, okay, the board. We can calculate the impact factor. We can calculate the impact force. Okay, we can actually calculate the maximum, right, sigma max now, and we can calculate a safety factor. All right, we can calculate how much displacement that board should have based on this force. So this is the max. This is essentially that delta impact we were talking about. We can calculate the gravitational potential energy we were talking about, mg times that quantity, h plus delta impact. Okay, we can then calculate also the impact energy. All right, well, actually, this is not, you don't need this. You can just calculate the strain energy, all right, because this is from the delta impact. And we can do these analyses, all right. Let's skip this little part back down here. Let's just focus on this from here to here. So when we run this, okay, so we're looking at the impact strain energy. Okay, so we're impact strain energy, all right. Okay, what we see is that there is a, so we're now looking at, okay, go back here. Okay, that was a static. So there's a significant factor of 10, all right, in terms of how much the force is increased, right? So 10 times that 686, all right, will get us to an impact force of about 6,652, all right. So it's not, not quite 10, 9.7, all right? And then the maximum bending stress we calculate is 93 megapascals from our analysis. We have a safety factor of 3.8, so that's good, right? Because it was 352 megapascals for the yield strength of the material, and now we're getting to 94 or so megapascals. The board below the zero line, okay, will go down about 260 millimeters, or 0.3 meters. We can think about the total gravitational potential energy, and we can also think about the strain energy in the system. Okay, so now let's think about how we do this simulation in Ansys. I would like to know these properties, get these properties when I drop someone from a height of 1 meter. Okay, that's the question we're asking ourselves. But I can't put in Ansys h equals 1 meter, right? I can't do that. What I can do is I can adjust the amount of force, all right, that we apply to the system, and then look at the strain energy and look at the displacement, right? If we go back to these equations, I can look at the strain energy, all right, and I can look at the impact displacement, and I know mg already. I can look at these two results from the simulations and then back calculate what h was, all right? So it's a little bit of an optimization problem. I have to figure out what force I'm going to apply to my system to get a strain energy and impact that gives me the right jumping height, or the right height to which the person achieved before they fell. So this is a little bit complicated and maybe not super intuitive, But what we're going to do essentially is we're going to guess, all right? But we're going to take some educational guesses, all right? We have a pretty good educational guess that if I put an h here of 1 meter from our analytical calculations, the impact force is going to be 6,650 newtons. All right, so that's a lot of newtons. So why don't we use that? All right, so we'll use something. Let's go, 6,000, 7,000. Right, we're gonna essentially change the amount of force that we apply to our static system in Ansys, and then see what h we get based on the quantities for the strain energy and the um, uh, impact displacement. Okay, so let's go, and we're going to use workbench data design points to do this. So let's go back here. What do we need to put into our system? Well, we need to put in a force. All right, so that's a good thing to parameterize. So we can click this. All right, and it's still at the minus 686. That's okay. We'll leave it there. Okay, and what do we need to get out? Well, we need to get out our deformation. All right, so that we can get out here. All right, and we're going to go ahead and take the maximum deformation or the minimum. Sorry, we're going to take the minimum right there, right? Because it's going to have a negative sign, but that's the minimum one that we want. And let's also look at our potential, our strain energy, okay? And so for this, we're going to take the total in the system like that. Okay, that would be millijoules, right? So once we've got all these parameters selected, we can go back, we can close this, okay? And we can then go back to Workbench, and we can look at our parameter setup, all right? Here, okay. Oh, and I would like to record the when it's also good to record the stress, right? So we know that we're not breaking the system. Okay, but for now, let's just use these. We can go back and do that in a second. Okay, so maybe let's try 6,000. Okay, newtons, and then we're going to make it minus. So minus 6,000. Okay, and let's try minus 7,000, okay, newtons, like that. And let's go ahead and say update all design points. Now, while this is working, okay, let me show you another MATLAB script. And this is just for the lab assignment, all right? What we're going to do is we're going to keep track of the force that we're applying, the strain energy, and the delta of impact, right? And see when we get to a height that's close to 1. So this H Ansys is what our objective. That's what we want to be 1. Okay, and so we're going to plug in different values. What have we plugged in so far? We've plugged in minus 6,000 and minus 7,000. Okay, so if we go back now to Workbench, let's see, did it solve one? It solved for 1. All right, and let's see, it's solving for the second. Maybe we'll let it do this. Okay, and while we're doing this, you might want to copy down some of this information. Okay, because this is where we're going to put our data in here. Okay, and then we're going to take our force and our delta impact and our strain energy. Okay, we got to make sure that they're the same because they might have come out in different orders. And right now we don't have a max stress, so I'm going to deselect that one. Okay, because we're not going to do that one for now, and we're not going to have a max effective stress. Okay, but we'll have the other two. Okay, so let's look at what Workbench spit out. Okay, so what we do? We can take all of these. We can select, hit Shift, and then down, down, down. All right, and I'm just going to do Control C, and I'm going to bring this over to here, and I'm going to copy and paste a Control V right into Ansys. Okay, so what do we got? The first column is in fact our our P, and I'm going to put a negative sign because those are negative, but I want them to be positive. So that's the first column. The second column is the displacement we're getting, so that's good, but it's second, so it's not 3, it's 2 now. Okay, so I'll put 2 there, and then the third one is the strain energy, and I'll put 3 here, and we're multiplied. These are in millijoules, or this is in millimeters, and this is in millijoules. So to get it in meters and joules, we're multiplying by 1 times e to the minus 3. This is that formula that we saw before, and let's run. Let's see what we get. Okay, so we do this, and what I've got here is it's going to just tell us what the drop height was for Ansys for the last point we simulated. Okay, and this is the plot. All right, so here are drop heights. When we plugged in 6,000, all right, we calculated a drop height of about 0.78. All right, and then we plugged in 7,000, we got a drop height of 1.1. Okay, so it's got to be somewhere in between. If we're going for 1, right, we can say, oh, it's going to be somewhere in between here. And right, when we did our analysis previously, we did get 6,600 or 6,700 or so, right? So this is lining up very nicely. For the task, what I'd like you to do is to put in another design point and figure out, okay, what's the force, all right, that's going to be associated with it. And then in the assignment, what you're turning in are the maximum deflection, all right, so that we're calculating out, right, and the maximum effective von Mises stress experienced by the diving board. So let's go back and make sure that we get Ansys to spit out what we want. Okay, so it is giving us the maximum deflection. Well, it's the minimum, but it's a minus value, right? And if we go back to our project, okay, we can go into the model again, and we'll ask it to give us the effective stress as well. And once we've gotten this value, okay, what we want to do is also take some snapshots, okay, take some screenshots of the beam, all right, and you can get snapshots of the appropriate stress, right? So you're going to want to get a snapshot of this. And for the deformation, I suggest that you actually go in here and you have it display at the true scale, okay? All right, so this, remember, this is using this modest, just the static load, okay, of the diver here, all right? So the deformation is not that much, all right? But when we start putting thousands of newtons, right, the effective force, we're going to see a much more significant deflection. We know it. It told us, right? We've got values that are, if we go back to MATLAB, we've got values that are showing, you know, hundreds of millimeters. Okay, so but let's just put in the parameter for stress. So I'm going to come over here to equivalent stress 2. This one was the one that we used on the top. And we're going to come down here and we're going to look for the maximum, okay? And that we're going to want to have it spit out for us. So when we come back over to our parameter set here, right now we see it's spitting out this parameter as well, right? So if while I'm running this, I'm not going to have, I don't think I'm going to wait for it to do it all over again, but now I'm going to uncomment this, and I'm going to say, oh, it's going to be the 4th column, okay, and I'm going to uncomment this, okay, and it's going to give us the von Mises stress, all right, and then I will copy and paste all those data again, okay, so I don't know if it'll let me do one. Sure, it'll let me do the first one. That's nice. Okay, so I'll just do the first one. Okay, like this. Control C, and then we'll go back to MATLAB. Okay, and I'll just delete all these. Okay, and Control V. oops, Control V, right, like this. Okay, so now I've got my 4 columns, and it's just going to plot 1 point in my figure, all right? But it will tell us, okay, yes, we got 10.41 megapascals, which is what we saw, and that agreed nicely with what we got previously. And this is that same plot, but now it's just 1 point. Okay. So the deliverables here are to, yeah, you may have a different height specified, all right, but from a height of 1 meter, okay, above the zero displacement line, all right, we've got to figure out what the maximum deflection is, okay, and the max, so that's what I would want you to tell me is what is the deflection of the board, right, and that's given here, maximum beam deflection, all right, but you're going to have a different value, of course, because you're going to apply much more force for the impact. We're going to have, here, we're going to share the maximum effective von Mises stress, so this is one on the top, not the one that is close to the fixed support, all right, and or on the displaced fixed displacement support, all right? And then I want you to include a screenshot showing the FEA for the deformation and another screenshot of the FEA showing the von Mises stresses and put them all in one deliverable. Okay, or one PDF, sorry. Thank you very much. Have a great day.